All right, what we're going to take a look at is formal charge and resonance. And anytime you are showing the movement of electrons or drawing the resonance structures, chances are things are going to change in terms of their formal charge. And really what it comes down to is what happened. Did something lose electrons around it, or did something gain electrons around it? And so let's look at this example. Draw this up a bit better. There. Now I'm going to draw a resonance form for this, starting here at these lone pairs. I'm going to move them down to form a double bond there. Now, so that I don't violate the octet rule, and what I'm going to do here is kind of review a little bit from the last lecture. I'm going to do something wrong. If I do this to move the double bond there, what is wrong about that? This carbon that I'm moving them to is sp3 hybridized. I can't move electrons towards an sp3 hybridized atom. I'd have way too many electrons around it. So instead, my second arrow, I'm going to move those pi electrons to that atom there that I drew because that's sp2 hybridized. So let's draw the result, and then we're going to draw in charges. So now if we take a look at the oxygen, that oxygen has a total of 6 bonding electrons around it and 1 lone pair. Again, review your chapter 1 lectures when I talked about how to easily recognize formal charge for some of the common atoms. That's going to give oxygen a formal charge of +1. Now, you don't have to put your charges in circles like that. I just like to do that because that helps me see, there's a charge there. So if you want to do that, fine. If you don't do it, you're not going to lose points. Now, the way to justify this is that oxygen lost a lone pair. It gave up a lone pair to make that pi bond. So that's why it developed a +1 charge. Now, the carbon gained a lone pair here, and so it will develop a negative charge. And I'm going to use this example to emphasize one more point about formal charge. What is the overall charge of the resonance structure on the left? It's 0. What is the overall charge on the resonance form on the right? Well, you have a +1 and a -1. That overall charge is still 0. So this is one way that you can check your resonance forms to make sure that your formal charges are correct, is that the overall charge for every single resonance structure you draw, whether it's 2, 5, 10, whatever it is, the overall charge for each one should be exactly the same. So let's do some practice with this. So in each of these, they're kind of telling you what the electron movement is. And so in A, we're moving these electrons there towards that sp2 hybridized atom. So if I'm going to draw a resonance structure for that, now the double bond is there. And what happens to this carbon right here? Notice it's missing a pair of electrons around it now. So it's going to develop a +1 charge. Again, the formal charge to begin with was +1. The overall charge to end with is +1. So that's a good way to check. Now in B, we're doing 2 movements here. We're moving this lone pair to form a pi bond here, and we're moving these pi electrons to that carbon atom on the end. So what does that resonance form look like? Well, now there's a pi bond here, and this carbon has a lone pair. Now let's deal with this carbon right here. Notice it gave a lone pair to make a pi bond. So that's why its formal charge is 0. I'm just going to kind of put it in parentheses there. You don't ever have to indicate that the formal charge is 0 like this. I'm just showing you that it's now 0, not -1. And this lone pair over here, I'm sorry, this carbon gained a lone pair, so it becomes -1. Now let's look at C here. So we're starting with this lone pair, going to move that towards that carbon, form a pi bond. So I don't violate the octet rule. I'm going to take these pi electrons and move them up to that oxygen. Now let's deal with charges. So let's start with this oxygen here. I'll just highlight it. Started out as 0. Now it has an extra lone pair on it. An oxygen with 3 lone pairs is always going to have a formal charge of -1. Now the other oxygen lost a lone pair. So it will develop a formal charge of +1. And let's look at the last one. So we're going to take this lone pair, move it to form a pi bond. We're going to take these pi electrons and move them up to the nitrogen. So if we deal with the nitrogen first, it now has an extra lone pair on it. So it will have a formal charge of -1. Now, what should happen to this carbon? I'm going to highlight it here. That carbon started out with a formal charge of -1. It lost a lone pair, or it gave up a lone pair, I should say, to form a pi bond. So now its formal charge is 0. And again, you do not have to indicate any, if something has a formal charge of 0, you don't have to write 0 next to it. All right, now let's spend a little bit of time looking at some very common patterns that you're going to see with resonance. The first of these is identifying what's known as an allylic lone pair. Now, allylic is a term used to kind of locate a special position that involves a double bond, specifically a carbon-carbon double bond. Now, the carbons involved in a double bond are called vinylic. That's just a side note. I might talk about that a little bit more in another chapter. Right now, what I'm going to focus is the first position outside of a double bond, a carbon-carbon double bond, is known as allylic. So all of these here, so that carbon is directly attached to a double bond, carbon-carbon double bond, is called an allylic carbon. So if there is an atom with a lone pair in an allylic position, that's going to set up a very common resonance pattern. So look at this structure right here in the middle. Comparing the two nitrogens, both of them have a lone pair. So let's look at this top one here. Notice there is no double bond. If I go this way, no double bond there. If I go this way, no double bond there. So just because there's a lone pair doesn't mean we can move it. Because if I try to draw a resonance form by moving this, like, oh, let's move it there, that adjacent. Can't do that because that's sp3 hybridized. And I can't do that because that's sp3 hybridized. But this nitrogen, the second one here, is in a allylic position because I have that carbon-carbon double bond, and the first atom outside of that is allylic. So I can do stuff with that allylic lone pair. I can take that and move that like this. And so I can now have a resonance form like this. That's a very, very common thing to do with allylic lone pairs. So we got a lot of examples down here. So here, there's our double bond. First atom outside of that, the allylic position, there's a lone pair. So a very common thing I can do with it is move that. And when I say move it, I mean using resonance. Now in the second one, again, identify here, we got a double bond. Just put parentheses around, there's our double bond. And the first atom, or one of the first atoms outside of that double bond, that oxygen, has a lone pair on it. Okay, this carbon doesn't have a lone pair. We don't really care about it. But this oxygen has a lone pair. And so a common trend is to use that lone pair for resonance. Now, the next three examples technically don't count as allylic positions, but they work exactly the same. The reason they don't count as allylic because it's not a carbon-carbon double bond. But we're going to treat this carbon-oxygen double bond, this carbon-nitrogen double bond, this carbon-oxygen double bond as if it were a carbon-carbon double bond, because the electrons are going to act the same way. I'm going to take a lone pair, move them towards that double bond, and move these electrons to that atom. Notice it's the same trend as the first two examples. It's just that technically, it's not an allylic position because it's the double bond that's there is not carbon-carbon double bond, but it acts in the exact same way. And we'll do that with the next one, with the nitrogen here. Take this lone pair, move it to form a pi bond, move these electrons up to that nitrogen, and there should be a lone pair on that nitrogen. You just want to draw that in. I'm going to kind of go out here with this. And now this nitrogen has the negative charge. Again, don't forget your formal charges. And then with this last one, I'll use the lone pair on the nitrogen as if it were allylic. And draw this as my resonance structure. Now, another kind of similar pattern is allylic carbocations. Now, carbocation, kind of put the name together, it's a carbon with a positive charge. Now, when that positive charge is in the allylic position, that is a very common thing to move electrons to. So I can use the double bond here. Use, I should say, the pi electrons in that double bond, move them towards the plus, the carbocation, and then the other one becomes positively charged. Since I moved electrons away from this carbon, it now has the positive charge. Now, I want to point out one very common mistake students make, and they make these all the time when they're dealing with positive charges. Notice I did not draw an arrow showing the plus charge moving over there. That's very, very wrong. Don't ever, so never Place the tail of a curved arrow on a positive charge. Why is that? Because a plus charge is not a physical object. Electrons are physical objects. A plus charge is the absence of something negative, an absence of electrons. And so it's literally just a hole, empty space. You can't move empty space. There's nothing to move. So that's why you don't show a curved arrow starting at a plus charge. Now let's look at this second example. So I'm going to just start here at these pi electrons and move them here like this. So now the positive charge is there. Now I can take the other pi electrons and move them like that. Same movement, just from a different pi bond. And now my positive charge is there. They say, well, can things have more than one resonance form? Yeah, it's possible. Sometimes there is only one. Sometimes there are multiple ones. And this is, again, a good thing because we're distributing that positive charge across multiple atoms. Again, there's an example of resonance stabilization. Now I'm going to go off on a little bit of a rabbit trail to highlight something important about this particular example. Is this represents what's known as a conjugated system. A conjugated system is a series of consecutive parallel p orbitals. Now, if I just draw the molecular orbitals or just say the p orbitals of this system, this carbon was sp2 hybridized, so it has a p orbital. This one has one, this one has one, this one, and this one. You say, why not the one on the end? Well, that one on the end was sp3 hybridized. It doesn't have an unhybridized p orbital. But I want you to imagine all those p orbitals being so close to line up and overlap with each other. Those consecutive parallel p orbitals form what's called a conjugated system. And those conjugated systems are a whole lot more stable than systems that are not conjugated. Keep that in the back of your mind. That's something that we will talk about a lot more at a later date. So let's do a little bit of practice here. Okay, so first thing we're going to do is just kind of recognize if this fits one of our trends. So we got a carbocation, and that carbocation is in the allylic position because it's attached, the carbon there is attached to a carbon-carbon double bond. So I'm going to show that those pi electrons moving over. And now the positive charge is over here. Now let's look at C. Notice the carbocation here again is allylic. Notice which double bond it's allylic to. It's allylic to this one, not this one. So why do I point that out? Because these are the ones I'm going to move first. So now the double bond, or I should say the pi bond's moved over, the carbocation is there. Now I can do another movement because now this new carbocation is allylic to this double bond. So I'm going to move that there. And then the last example, again, we got a allylic carbocation. In this case, that carbon is allylic to this double bond or this one. So I could start on either of those. I'll just start with this one here. And let's get some practice drawing a 7-membered ring. So now the plus charge is here. And then I can move this one here. And the plus charge is here. And I'll do one more. I can move this one here. And the plus charge is there. A third common pattern is a lone pair next to a carbocation. And that lone pair could be on a variety of different atoms. So the key thing here is to recognize the pattern of the lone pair next to a carbocation. So let's look at this, for example. So notice this atom has a lone pair and it's next to a carbocation. So I'm going to take one of those lone pairs and move them to form a pi bond. Always forming a pi bond. Notice I'm not drawing that arrow to go to the carbocation. I'm using it to form a pi bond. And let's just look at like the formal charges. Notice the oxygen started out -1, but it gave up a pair of electrons to make that pi bond. The carbon was +1. Now it has a full octet, so it has a formal charge of 0 as well. Let's look at another example. So we have a carbocation there. The atom adjacent to it has a lone pair. So I'm going to use that lone pair to form a pi bond. Now that oxygen gave up a lone pair to form that pi bond, so it now has a formal charge of +1. Okay, so let's do some examples. And the first thing we're going to do is fill in lone pairs. So in letter A there, that nitrogen's got a lone pair. And that lone pair is next to a carbocation. So I'm going to do one of the common things I can do with that and move them towards that carbocation to form a pi bond. So now there's a double bond there. And the nitrogen now has the positive charge. Nitrogen with no lone pairs on it, so total of 8 bonding electrons, no lone pairs, has a formal charge of +1. Now let's look at B. First thing is we're going to draw in the lone pairs on the nitrogen. Now it's shown there that the nitrogen is negatively charged. How many lone pairs does a negatively charged nitrogen have? Should start out with two lone pairs. And the common pattern, move it down to form a pi bond. And since the nitrogen lost a lone pair to form the pi bond, its formal charge is 0. And the carbon gained a pair of electrons around it, so its formal charge is +1. I'm sorry, neutral now. It went from +1 to 0. And then let's look at C. So oxygen should have 2 lone pairs. A neutral oxygen should always have 2 lone pairs to it. And I'm going to follow the trend and form a pi bond. Use that lone pair to form a pi bond. And now since it only has 1 lone pair left, it has a formal charge of +1. Finally, the last common pattern, and these aren't the only things you'll ever see do resonance, but these are like some of the most common patterns that you're going to see. Probably, if I were to put a number to it, I don't know, like 95% of the time, you're going to be doing one of these 4 things. And that's if you have a pi bond between atoms of differing electronegativity. So let's look at that carbon-oxygen double bond here. You got carbon, you got oxygen. If you look at the periodic table, hopefully you remember your periodic trends. That was one of those things that I told you to review at the very beginning of the semester. Oxygen's a lot more electronegative than carbon. So if I'm going to move these pi electrons towards either carbon or oxygen, which one should I move them towards? I'm going to move them towards the oxygen. In fact, let me show you something wrong right now that you never want to do. I'm never going to move these pi electrons to the carbon because that puts the negative charge on the less electronegative atom. So I'm never going to show that. So when I draw the resonance form, I always move the electrons towards the more electronegative atom. And it's the same thing for nitrogen. I'll use those pi electrons to move them towards the nitrogen. And just remembering my formal charges. All right, let's do a few practice on this, and then we will stop for this part. So in A, first thing I'm going to do, draw on a lone pair. Again, nitrogen with a total of 6 bonding electrons is always going to have 1 lone pair. Now it's like, well, there's no carbocations, there's nothing allylic, like there's nothing I can move. You can always, so if we have 2 atoms that have different electronegativities, we can always move those pi electrons up to the more electronegative atom. And nitrogen becomes negative, the carbon becomes positive. All right, for this one, again, only thing I can really do is move pi electrons to the more electronegative atom. So that's what I'm going to do. So oxygen gained a lone pair. Anytime you see oxygen with 3 lone pairs, always -1. And that carbon lost electrons around it, so it now has a formal charge of +1. And then finally with C, again, only thing we can do here is move the pi electrons in that double bond towards the atom that is more electronegative. So in this case, I'm going to move them towards the oxygen. So the oxygen has a formal charge of -1, and the carbon that lost the electrons has a formal charge of +1.